Good morning, everyone. Welcome to our lecture. Before we get started with our lecture this morning, I want to make one announcement regarding Chapter 4 quiz. Some of you, you may have received a notification regarding quiz number 4. It is available until Tuesday next week. You have 1 week, or you had 1 week actually to complete. You should be done by next Tuesday. I will post a study guide, what you need to focus on before you log on to take the quiz. I think it's about 30 or so questions, and you have about 90 minutes. More information will be sent. I will share the information regarding quiz number 4. Please don't get started until when you look at the material, what you need to know. I will send you information regarding what material you need to have. For example, periodic table, the solubility chart, which I posted in module number 4 to predict the precipitation reaction, okay? So bear in mind that our quiz number 4 is available due next Tuesday. You have until midnight on Tuesday to take that quiz. More information will be shared for those who are not with us this morning and for those who will join us during the course of the lecture. If you are not here last week, we started chapter 4. We completed chapter 4 and started chapter 5, thermochemistry. And thermochemistry is basically the study of chemical reaction which produce or which give or absorb heat energy. All right, and we talked about the internal energy, which is the sum of potential energy and kinetic energy. We talked about the potential energy plus kinetic energy gives what we call the internal energy. And change in internal energy is calculated by, all right, is determined by sum of, all right, there are two equations which is used to calculate the internal energy. You look at my whiteboard. Change in internal energy is obtained by E final. This is what we talked about last time, minus E initial. Remember what we talked about, the internal energy being state function. It only depends on the final and the initial, and you can calculate internal energy by using the given equation. Now, let me see, I don't think you are seeing my screen. Let me share my screen here. I want to share my screen so that you can, I don't think you can see my screen. I want to share my screen, that way you can see my whiteboard. There you go, all right? There you go. That is what I wanted to show you in terms of the equation used to find the change in internal energy. We talked about the state function depending on final and the initial. There is, you got to know the sign convention for delta E. If it is positive, it's given off. If it is negative, it's given off. Internal can be positive, negative. E can also be determined using the this equation Q, which is heat, plus W, where Q is the heat, this is the heat energy, and W is the work. All right, it's the sum of the heat and the work. you got to be familiar with the two equation. When do we use that? The heat energy plus the work, and the sign convention which goes with the Q and W. Remember exothermic. I know you can relate to this, and remember the system isolated, you know, all those. Let's see. For our system, which is the forecast, in this case, is where the reaction is taking place. Going to see, Q can be what? Q can be negative, all right? It can be negative if it is being given off. This means negative, this means positive, carrying into the system, or work also could be positive W, or it could be negative W, so that when you plug in this equation, you should see the final sign of Q depending on the sign for Q and sign for W. You may not see, all right? You may not see in the equation the negative and the positive sign here, but the work done by the system, for example here, work done by or work done on. Work done, that means it's getting out. Work done on is getting in. Heat given off is negative. Heat being absorbed, you know, or heat from the surrounding, that means positive. Heat to the surrounding, that means it's negative, and so forth. You got to know that. Now, we had actually, on this equation, in this equation, we stopped at this component of internal energy. This side, this is where we are right now. And there was an example here. All right, look at the PowerPoint slide here. There was an equation we solved on the work, calculate the work in joules if the volume of a system contract, all right, from 1.55 liters to 0.85 liters at a constant pressure of 0.985. At the outset, this W is determined using the equation here. W equals to negative pressure times change in what? Times change in volume, times change in volume. This is always in what? This is always in ATM. And this is determined from this equation, V final minus V initial. You have to calculate that. Sometimes you may be given a statement, change in volume by this, and then delta is given. So depending on what you will get from here, it can either be negative or it can either be positive. So if it is negative, then negative times negative gives you positive. If it is positive times the negative on the pressure right here, it will change to positive. Those are the things you need to know, all right? Final minus initial. Is it positive value? Is it negative value? So that when you plug in there, you'll end up with that. Now, in this example, we use the equation work is given by negative 0 point, pressure is 985. Look at the units, ATM times change in volume. Change in volume is final, all right? Final minus initial. Don't make it positive by subtracting 1.55 minus 0.85. So 0.85, which is final, minus initial 1.55. I see it's negative, what? Negative 0.7 liters. So if I multiply that by 0.985, this is negative what? This is positive 0.6 895, and it is liters times atmosphere, liters times atmosphere. You cannot just assume that it is in joules and just, you know, it could be one of the multiple choices in joules and you think that I used the right equation. Why don't I just say 0.6895 joules? No. There is a conversion factor which I'll give you, and you should know. Maybe you're not seeing you will not have when you're doing the homework, but it turns out that 1 liter times atmosphere equals to 101.3 joules. This is the conversion factor you will need to convert the given value in liters atmosphere. So I'll just have 0.6895 liters times atmosphere times, you want to get rid of 1 liter times atmosphere, and you remain with joules, 103.3 joules. So 0.689 times 101.3, and this is 69, I see it's 69.85 joules. So 4 significant figures. Sometimes they might ask you in kilojoules. You have to do that. Andrew, how did you get 0.7 for again? Did I say 0.74? Let me see. Let me go back. Did I say 0.74? No, this is liters, not 4. This is liters. It is final minus initial. Let me see. You see, from this equation, Andrew, from this equation for calculating, look at my whiteboard, from the change in, remember this is the equation for calculating work, calculate the work in joules. Given this, negative P, pressure should be in atmospheres. You can change that because of this. Because of this, you need to change the pressure to atmosphere. So, final minus initial, that's where I got it. It's not 0.74, so my stylus sometimes doesn't really work well. So that is what it is. Thank you. Oh yeah, you can. So we're good to go. All right. We are all on the same page. So that is what you need to remember. The final minus initial. I've seen some questions. Volume might be in ml, but you have to remember that 1 liter equals to 1,000 ml. They might not give you that, but they expect you to remember. They expect you to remember. I don't know if you'll be expected to remember from Introduction to Chemistry that 1 atmosphere equals to 760, TORR equals to 760 millimeter mercury, which is equals to 14.7 psi. All right, these are just equivalent statement for converting the pressure to atmosphere. So depending on the units, you got to know that. Do we have to memorize the conversion? I think, Deriana, I think you are asking about the equivalent statement here. I'll give you in the test because it's time sensitive, but in the event that, you have to study for homework, you'll not see in the homework assignment, for example, and you may be like, how do I get this? Or why am I not getting this? Is because you need to know that. All right. Don't memorize this. I'm just going to give you this, but in the homework assignment and probably in the quiz, you have to know. In the exam, I'll give you equations and constants. All right, so that is what we are supposed to do in this. Remember, PV work. That's what I want you to know, where we are in the internal energy. How do we calculate work? And what can be positive, it can be negative. Just plug in this equation, and everything will play out right, positive or negative. Don't worry whether it's positive. Remember, what can be done on the system can be done by the system. Now, in this equation right here, we're gonna talk about this momentarily. That is the heat. Q stand for the heat given by or absorbed by the system. Okay, the heat. So I want you to pay attention to the wording done by the gas. That means expanding. Done on the system, all those. It's just gonna play out when you plug in that negative, because work is done by the system. If it is positive, that means work is done on the system. Positive, that means work is done on the system. This means on the system. I see some trick questions sometimes, multiple choice, that you have a positive value, but they say which one of the following is true when this and that are, and then you do the calculation, and then they say, oh, the work done by the system will be this, or the work done on the system. You have to go by the sign convention. Rewrite the notes again on your own until you master. Do more problem on work component on internal energy. We are now shifting gears to Q. Remember Q? Q on internal energy stand for the heat. And in section 5.3, enthalpy. Here, it may sound like, exoteric term you don't know, but just from what you know, enthalpy like that, this is heat of what? Of reaction, heat of reaction, just heat of reaction. And we denote this using the notation H for enthalpy. I don't know why, we don't use E for enthalpies. Could have made sense to use E, right? But E is for internal energy, H is for enthalpy of reaction. And when you see this, you'll see this down the line. This means change in what? Change in enthalpy, all right? Which is simply change in heat of reaction, change in heat of reaction. So if it takes place at a constant pressure PV work, we can just talk about the enthalpy, and it is obtained by the internal energy we talked about last time. From this, enthalpy now is internal energy plus PV work or change in volume. PV work, this is the same thing, change in volume. This is work or internal energy we talked about last time. H is change in internal energy plus change in PV. So if we have change in internal energy, change in volume, and change in internal energy for a system. I don't want to just spend time on how to calculate change in enthalpy using this equation, but what I want you to know is this is in place of this we will be using Q. This is the same as Q. Look at this Q. It stands for the heat, so we can also this means heat of reaction. All right, heat of reaction. And there is also an equation for this, which you need to know. If heat is gained, if heat is lost. Remember, exothermic and endothermic reaction. If heat is lost, exothermic. If heat is gained, endothermic. So at constant pressure, sometimes you see this subscript P means constant pressure. We can calculate the heat gain by the system or heat loss by the system, exothermic, endothermic. I can use this. I know we had this before. Negative means exothermic reaction. And this is the system right here. And positive Q means thermic reaction. Endothermic reaction. It is given off, it is absorbed. You know all those terms. Exo means getting away. Endo means it is being endo, it is being gained. Exo, it is being lost. I want you to pay attention to this symbol right here, because you will see in the equation anything greater than 0 is positive. You know, from the number line, anything greater than 0 is positive. That is why I have positive here. So I can have here, you can relate this, that it means also delta H is greater than 0. Anything greater than 0 is positive. Anything less than 0, anything less than 0 is negative. That is what is meant by or these two terms right here. Okay, what does this means? Means positive value, and this means negative value. When you see in the equation, you should understand what they mean, if it is exothermic, if it is endothermic. This is a typical question you will see on the conceptual. You don't need to do any calculation. When a reaction occurs in a flask, you will notice that the flask gets cold. What is the sign of delta H, change in enthalpy? Somebody try. What is the sign if the flask gets cold? It's getting cold. If you hold it, it's cold. Is it exothermic or endothermic? From there, what do you expect the symbol for delta H or change in enthalpy? Somebody is saying it's getting cold. No. The correct answer is endothermic, which means it is positive. You see, to understand or to answer such questions, you have to first of all figure out where the system is. Always what I've seen in concluding this is put yourself in the system. All right, let me use this analogy. If this is the flask, I'm holding it and I feel it's getting cold. It's getting cold. So that means the heat from my hand is getting into, it's absorbing the heat from the surrounding. It's not only coming from my hand, even from the lab or from wherever, from the surrounding. Remember the surrounding, when we talked about last time, that surrounding is what? Surrounding is right here. Surrounding is right here. This means when I hold the water bottle, it's getting cold. That means it's absorbing heat from the surrounding, and the system is in there. That is where the reaction is taking place. Read the question. When a reaction occurs in a flask, so this is the flask, and when I hold, it's getting what? It's getting cold. It's absorbing heat from the surrounding, and endothermic, which is positive, If you fail to understand where the system is, you will not know. If I hold an ice cube and it's get cold, the ice cube is the system and it's getting in there. Heat is getting in there, means the heat is gained. And the correct answer is A, not B. B, that means it's getting hot. So if it is exothermic, remember exothermic is negative. If it is exothermic, I should feel it's getting hot and hot and hot and hot. Just the way when you hold a coffee cup, well, with the sleeve, you still can feel that the coffee is hot. The coffee cup is hot, right? So that's what you need to know. And it goes back to the sign convention. Let me go back again one time here. If you look at this sign convention, heat gain, that means it's gonna be positive. Positive being gain. Exothermic, all right, heat being lost, exothermic, that means it should be negative. It should be negative. So if I hold, it will feel cold because of that. So the correct answer is A. Now, a chemical reaction that gives off heat to the surrounding is said to be dash and has dash value. You got to be careful with that question because you may only get the first time here, all right, or you may get the correct time which complete this space here, but the value for the second space might mess you up. I've seen problems similar to this. Somebody saying that this is what it is. Yes. Andrew says D. Let's see if it's correct. So exothermic is giving off. That's correct. And has a negative value. Yes, correct. You're right, Andrew. Thank you. The correct answer is D. Anybody had a different answer? Maybe we can see, or I can explain to you why it's not A. Endothermic. This should be positive. I mean, exothermic, giving away heat. Endothermic, absorbing. So off, you gotta be careful with the terms used in that. So correct answer is D. Correct answer is D for that. Now, change in envelope, endo getting cold. Endo, yes. Endo will get cold if you hold it, yes. It will get cold. And it will have positive, you know, it will be like, if you look on the whiteboard here, this is endo. It will be positive, not negative. It's gonna get cold, but yes, correct. Antonio, it's gonna get cold. Let's see how to calculate the enthalpy of reaction in the lab. Change in enthalpy of reaction. Can be determined when you see the enthalpy of reaction here. Let's see, change in enthalpy of reaction. This means, look at the subscript. RXN stands for reaction. Enthalpy of reaction is given by, I don't like the equation the way it is here, but let me remodify this to this, right? Summation of M enthalpy for product minus summation of enthalpy of what? Change in enthalpy of reactants. In the equation in the PowerPoint slide here, you may not see the M and N. This M and N are what? Are coefficient in the balanced equation or balanced equation. There are thermodynamic terms in the text which gives you the you know, the terms for product and reagent. Where is this equation coming from? When we say product and reagent, it's with respect to an equation. It's with respect to an equation. Here is the reaction. Methane reacting with oxygen gas to produce carbon dioxide and CO2. What I have on the my whiteboard here, M and N, these are the coefficient in the balanced equation. If you look at the methane and oxygen, these are the reagents. So we will have to find the summation, and that's why I have this symbol. I don't see the summation sign. So I'll say for product, these are the product. I'll have to look at the enthalpy of formation of H2O times 2, because we have to in for H2O. And then carbon dioxide, I gotta look for carbon dioxide. These terms, they are given in the terms, thermodynamics terms, they are given in the part, there is the Abedex with those thermodynamic terms. If not, you'll be given for particular reagents. In the event that you will come across in the homework assignment, I'll recommend that you look at the Abedex in the text to see those thermodynamic terms. I see on Abedex what we have on Abedex page 1 on what starting Abedex C, page 1088. All right, you'll see those thermodynamics terms delta H for the reagents, and product, and then you plug it in the equation. This is the equation you need to remember, and this means summation. I know some of you may not remember this means summation. You add all of them. So I'll check for product, I'll check for reagent, and I add, and then I'll get the enthalpy of reaction. Okay, enthalpy of reaction. General is given in, this one is given in kilojoules, units here, all right? Always units right here is units in kilojoule per mole, all right? Kilojoules per mole. The reason why I'm bringing up this is so that when we get to Chem2, there is another thermodynamic term given in joules, and you have to add them together, but the rule of them is the units are in kilojoules. You see kilojoules, kilojoules. Even for other equation, it will be in kilojoules, Here is another example. If you are to write the enthalpy of reaction or heat of reaction, product minus reagent, we need to find the enthalpy of H2O. And by the way, you got to pay attention to the physical states as well. If you look at page 1088, you may have enthalpy of formation of H2O in gaseous state, in liquid state, or in solid state. We can have a solid ice. So which one are you going to use? You're going to pick a value which corresponds to the physical state in the given equation. So in this case, I'm gonna look for H2O in gaseous state multiplied by 2 minus the summation of for hydrogen gas times 2, and then add for molecular gas, and then I add all of them. Sometimes it's 0, it's okay, all right? It's okay, and then you find the difference to get the enthalpy of reaction, using this equation right here, there are 3 points you need to remember about enthalpy of reaction. One, it is an extensive property. Remember, extensive property means a property which depends on the amount present. Volume, for example, all right? Volume, for example, is an extensive property. If I have 5 ml and 1,000 ml, they are not the same. Even though we're talking about volume, it is expanding. Area of a piece of paper, area of a yard, you know, is an extensive property. Enthalpy is also an extensive property. That means it depends on the amount of reagent in a chemical reaction. If you have less amount of reagent, and then less amount of heat will be given off or will be absorbed or heat in that case. So rule number 1 has to do with the amount of reagents, amount of moles involved. That's what we need to understand in rule number 1. It depends on the amount of matter present. Enthalpy change for a reaction is equal in magnitude but opposite in sign if we reverse the reaction. Yes, if you reverse the reaction, the sign will also change. So remember when we flip, especially when we be talking about the Hess's law, if you change the equation, that means you flip the product to be the reagent and the other, and vice versa, the symbol will change for the equation. And then enthalpy also depends on the physical state of the product and reactant. What do we mean by state? Is it solid state? Is it liquid state? Or is it in gaseous state? You got to pay attention to those terms. Now, what effect do these changes have on change in enthalpy for a reaction? Multiplying the coefficient on of an equation or of the equation by for the reaction pi2. If we multiply pi2, there is no change. The sign of enthalpy, change in enthalpy changes, the value of enthalpy doubles, and the value of change in enthalpy decreases by half. What effect will it happen if we multiply pi2? For example, here is a reaction I meant to say hydrogen gas reacting with oxygen gas to produce H2O, all right? And if I have a 2 there and I have a 2 there, suppose I have 4 hydrogen gas plus 2 oxygen gas to produce 4 H2O or liquid. This is liquid. What will happen to enthalpy of reaction if I multiply pi2 the equation? That's what is question mean, multiplying the coefficients of the equation for the reaction pi2. This was the original equation. If we multiply pi2, what will happen? Yes, Jennifer, correct. You are absolutely right. The value of change in enthalpy of reaction will double. It's extensive. It depends on the amount. So if I divide pi2, it will reduce pi2. If I multiply pi3, it will triple. If I multiply pi4, it will quadruple and so forth. So it has to do with point number 1 here, that that it is an extensive property. So we are multiplying pi2 and the enthalpy of reaction will double. Now, hydrogen peroxide can decompose to water and oxygen gas by the reaction. You are given the equation, all right? Calculate the enthalpy of heat released when 5 grams of peroxide decomposes at the constant pressure. What this also calls for understanding that enthalpy of reaction is extensive property. And when you read the balanced equations, I just saw it on the screen. Let me interpret for you before we solve this problem. This means when 2 moles of peroxide decompose, this is how much it is given off. Remember, negative means it is given off. That is what I was saying. This means it's exothermic. That means when 2 moles. If 1 mole of peroxide decompose, that means I will reduce this by 1/2. All right, Andrew, let me see. Yes, it should be H2O. Yes, you're right about that. Let me change that to H2O here. Andrew, you're right about that. This will be H2. No. I mean to say, let me just undo that. And I mean to get rid of that. And that should give us the right equation. Yes, that is correct. It should be liquid And what I was saying that if 1 mole of peroxide decomposed to produce liquid H2O, thank you, Andrew, for correction, it will produce it. If I divide by half, it's gonna give me that. If 1 mole of H2O is produced, and then we're gonna change that. So what this problem, understanding that concept, we need to find how many moles we have in H2O. In other words, this is for every 2 moles. What is the molar mass of peroxide? H2O2. Google out and give me real quick. What is the molar mass of H2? I know you have a smartphone somewhere next to you. Somebody Google out molar mass of H2O2. Let's all participate. Somebody give me. I'm giving you a hint on, how you can find out the molar mass of a compound real quick. What is the molar mass of peroxide? Thank you, Jennifer. Thank you. Yeah, it doesn't really matter whether you use for significant. See, Pethyhood, you gave me 34.02. Jennifer, you gave me 34.014, depending on which significant figures you want to. So this is the molar mass of peroxide. 34. Let's use 0.2 here. This is grams per mole. This grams per mole. So we will find out. The number of moles in 5 grams of peroxide using the molar mass as a conversion factor 34.02 grams of peroxide. This is 1 mole of what? 1 mole of peroxide, like that. Now, from the thermodynamic equation here, you have to generate a conversion factor based on what I explained to you, what it means when you are given in this. So if I cancel this and cancel this, watch what will happen what I'm going to generate the conversion factor. For every 2 moles, this is not molar mass. For every 2 moles of peroxide that decompose, all right, this is how much it is given off. Negative 196 kilojoules. So that mole and mole will code, not the value. That's how you generate the conversion factor to find the quantity of heat given in kilojoules. If I had 4 here, and then I'm gonna put 4 here. If I had 5 here, I'm gonna put 5 here. If this was positive, I'm gonna put positive at the top right there. Be careful with the sign convention, because you may have the same numerical value, but the sign will be different. So that is 5 times 196, all right? Divided by what? 34.02. Divided by 2. I'm just dividing, and I see that this is 14.4 joules. 14.4 joules is given off. This is negative. I don't know. I've used different text. And the wording might make a difference. For example, I can say this is the amount of heat evolved. Or sometimes they might say heat release, all right? So this is the heat release, negative 14.4 joules is exothermic. It is exothermic. So the point here is you have to use the equation to generate your conversion factor. The importance is, what does the equation means? What does this thermodynamic before you plug in the equation? All right, any question? So remember to read the equation and get that. That is the heat of reaction. There are 2 there are two equations you'd use for determining the, the heat of reaction. Either you are given a thermodynamic equation, or you are given the heat of formation the way I gave you. I didn't look in details into that, but remember that which equation you are going to use. What I mean by that is somebody might think that for this, let me try, let me show you. For this, somebody might think that, oh, where I need to use this because I'm going to give you this equation in the exam, and you're like, how do I relate this equation to this? How do I relate this equation to this? No, this has to do with understanding this, understanding what we talked about right here. All right. I didn't solve problems on this. Please solve on that. There's some equation on how to find product minus reagent, product minus reagent. Let's shift gears to what now we do in the lab. I know if you are taking the course, or if you are taking the lab section for this course, you may have done an experiment on calorimetry. All right. And what is calorimetry? Calorimetry is simply the art or science of determining the heat of reaction. All right, heat evolved during a chemical reaction using a calorimeter. And in the lab, a calorimeter is simply an insulated coffee cup. I don't know if you can see my my transparent cup right here for for my Chem2. Can you see that? Jennifer, can you see that? Can you see my two cups? So, not really. All right. Let me see if I can have a background. Can you see that? So, if it goes in and out, oh yeah, never mind. But picture that you have a coffee cup, you insulate similar to what you have, and the risk insulation is to avoid the heat ping, or when I hold with my hands, I don't want to transfer heat into the reaction vessel and the temperature will go up. All right. The calorimetry in the lab is simply insulated coffee cup, and this is the reagent. The starter here is to mix the solution so that the solution will have uniform temperature throughout. So as calorimeter include the temperature measurement, there's the thermometer, the stirrer, stopcock, and all this. And if the reaction is exothermic, it will give away heat and the temperature will rise up. If the reaction is endothermic, the temperature will drop and you will see a decrease in temperature. This is a calorimeter. And how do we determine the heat of a reaction? How do we calculate the heat of reaction? Heat, remember, heat, which is Q, is given by the equation here is this stand for heat in joules, is given by the mass, and always this one is given in grams, times what we call specific heat, and this is given in joules per gram times degrees Celsius times change in temperature. Change in temperature, this is given in degrees Celsius, and it's obtained by T final minus T initial. What is on this slide here, we need to differentiate between the heat capacity and specific heat of a substance. Specific heat, all right, here specific, let me abbreviate that. Specific heat is the amount, right here, amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. It's the same thing. 1 degree Kelvin or 1 degree Celsius is the same thing. This is 1 degree Celsius. That's how you define the specific heat. The specific heat, well, how I commit to my memory or memorize the definition of specific, you specify the amount by saying 1 gram. 1 gram. That's how I rewrite the amount of heat energy required to raise the temperature of a substance by 1 degree. All right. This is 1 gram. Whereas, all right, whereas heat capacity is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. So Christian is asking, go one slide, whiteboard right here. Let me go back right here. Same or this one right here? We will calculate the heat. This is the heat. Where we are going with this equation right here is relating to this right here. This is where this equation came in. That how do we calculate the heat using a calorimeter? If we know the mass of the reagent in grams and the specific heat of our solution here, and the change in temperature from final minus initial, we can calculate the heat given of in a reaction. I'm going to come back to that. I hope this is the slide you are referring to as where we're going with this equation. In calorimetry, we can calculate the heat given in joules using this equation. We're going to come back to that, and that's why I'm going to break down. I know you know the mass, right? Measure the mass of a reagent in grams. It's not something new, but specific heat, that is where I was explaining here that it is the amount of heat required to raise the temperature of a substance, 1 gram of a substance by 1 degree. You specify the amount. Whereas heat capacity is simply heat capacity here. Heat, it's not specific. Heat capacity, it's not specific. Is simply amount of what? You define this as amount of heat required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Here in heat capacity, you do not specify the amount, all right? The amount. Now, when we say molar heat capacity, that means the heat required to raise 1 mole of a substance by 1 degree. You're gonna talk about the molar heat from the word mole. We talked about the mole before, all right? The amount of heat or amount of energy, heat energy. Yes, sorry, I didn't say heat energy. So energy, it's the same thing. Heat energy. Yes, heat energy. Thank you, David. It's amount of heat energy required. So it should be the same thing here. Also heat energy. All right. You're making your own notes. It's the heat energy required to raise the temperature by 1 degree Celsius. Here is the, table 5.5, few specific heats of just few selected substances. If you look at here, the specific heat is given in joules per gram Kelvin. This is multiplication, and that is why in this equation, I gave you that the units will always be in joules, because grams and grams will go away, and degree and degree will go away. You are left with only joules, and this is the joules given because of that. Do you need to memorize the specific heat? No, you don't need to memorize. Unless you are asked to calculate, you will be asked to calculate the heat or if you are given one identity, if you look at this, there is 1, there is 2 here, there is 3 here, and there is 4 here. If you should be given 3 to calculate the fourth one, this is 4 right here. The last one is 4, and you'll be asked to calculate either the hit, either given the hit, calculate the specific, and remember mass has to be in gram, all right? It has to be in gram. If you look at the specific hit of water, for most calculation you will encounter hit of neutralization. Remember neutralization, H2O is produced. So if we are to calculate the hit of neutralization in joules, we got to know the mass of the reagents. A specific hit of H2O is given here. Then we plug it in the equation to calculate the hit of the solution. Solvent on a solid. C stand for, here, C stand for specific hit. You may see this and you're wondering what is this? It's the notation for our case. This is a specific hit, and the unit is joules per gram times degree Celsius or Kelvin is the same thing. Times the mass of the solution times the change in temperature. Remember, change in temperature is given. Look at the whiteboard. It is given by T final minus T initial. You may end up with a negative, you may end up with a positive, and if you know the negative sign, what this means is the reaction is exothermic. The reaction is exothermic. Let's see an example on how to, use this equation to do calculation or determine the heat given off when octane, all right? The specific heat of octane in liquid form is this. This is the specific heat. How many joules of heat are needed to raise the temperature of 80 grams of octane from 10 to 25? So at the outset, you should know that heat in joules is given by mass times the specific heat times the change in change in temperature. This is 80 grams times the specific heat of octane, given as 2.2 joules per gram times degree Celsius. Don't worry about Kelvin, it's the same thing, don't change to, all right? Don't change to Kelvin and then you say because of the Kelvin, it can either be, change in Kelvin will be change in Kelvin. It will not affect anything. Times what? Change in temperature is 10.0 degrees Celsius. If I reconcile the units, degrees Celsius will go away with degrees Celsius, grams and grams will go away, and we are remaining with units in joules. So 8 times 2.22 times 10, all right? 8 times 2.22 times 10, and I have 1776 joules. All right, I have the answer in joules. You may be asked in kilojoules, or they may not ask you, but multiple choice might be in kilojoules, so you divide per 1,000. All right, and 3 significant figures you may see in multiple choice, maybe 1, 7, 8, 0 joules. Why am I doing this? This is 3 significant figures. Sometimes they play with the significant figures. We have 3 significant figures, 3 significant figures, 3 significant figures, all right? Why is it 10 degrees Celsius? Is it, 15, it should be 15, I'm sorry. Yeah, you're right about that. Should be 15. This is just overdrive. This is 15 right here. 10, 25 minus. So that means it will change my equation here. Thank you. Using my calculation here, 80 times what? 80 times 2.22 times what? 15. Okay, it is 2.664 joules, and 3 significant figures, 660. All right, joules, and you can make it kilojoules if you want to. 25 minus 10 is 15. That is why we have to make that 15. Tyler, yes. Thank you. It's 15. Final minus initial. And then you plug it in the equation. If you are to ask to find in kilojoules, and then you divide, or you divide by 1,000. Divide by 1,000. So to find the heat of reaction, for pump calorimeter, this is similar to the coffee cup calorimeter, except that this one is an isolated system. Remember, open system, remember, closed system, an isolated system. This is an isolated system because neither mass or heat is lost. We can determine the heat in pump calorimeter using this equation where Ca, this is the heat capacity, all right? In pump calorimeter, all right, pump calorimeter, we use this Q for the reaction is given by, because it's combustion, it's giving away heat, cal times change in temperature. I know you know this from the previous section, T final minus T initial. This is not, the C here is not heat capacity, it's not specific heat capacity, but it is just heat capacity of calorimeter. Heat capacity of calorimeter, and plugging in that, you should be able to find the heat of reaction where the sample is placed in one. And if we know the heat given of, and we know the heat capacity of the calorimeter, we don't need to use the mass. You should be able to find the heat in the reaction for an experiment for pump calorimeter. For pump calorimeter, the equation given in there. For heat capacity of a calorimeter, you'll be given that. Let's see if the first equation or second equation will be applicable for this. When 6.5 grams of sample of solid sodium hydroxide dissolved in 100 grams of H2O in a coffee cup calorimeter, the temperature rises from 21.6 to 37.8 degrees Celsius. Calculate the quantity in kilojoule released in the reaction. All right. The first part right here is Q is given by mass times specific heat times change in temperature. This is T final minus T initial. T final minus T initial. This is the mass this is the specific heat of H2O, specific heat of H2O. Or you could ask me, how do I know, all these terms? Well, and you will see even in neutralization reaction, specific heat of H2O is used. Even when something dissolves, in this case, sodium hydroxide, the specific heat of H2O is used in calculations. Assume that H2O, and the mass of H2O is the mass we are going to use to calculate the heat evolved. And in this case, since we have 100 grams of H2O times the specific heat of H2O 1.184 joules, all right? This is grams times degrees Celsius times the change in temperature. If it rose from 21.6 to 37.8 minus 21.6, it should be 16.2. This is 16.2 degrees Celsius. This will go away, that will go away, that will go away. Oh no, this will go away, that will go away. Mass of H2O will be used, and multiplying this 100 times 4.184 times 16.2, 16.2. No, 16.106 mass of the solution, 106.5. This is 106. This is if the mass of the solution here, mass of the solution, 106 point. This is 106.5 grams of solution, because in a solution, the temperature of the solution 106.5 comes from the sum of the sodium hydroxide and H2O. And you should have 7218.65. This is joules. That is joules. If we divide by 1,000, make it kilojoules, 7.2. 7.23, 7.23. This is 7.2 kilojoules, 7.23 kilojoules. Now, divide by, if we are to find using the result from part A, calculate the enthalpy change of sodium hydroxide. Yes, Andrew, so whenever you are doing problem like this, you have added sample. Yes, to make a solution, you have to add the H2O and the mass of the sample. So not only this, even when you get to neutralization, where you have an acid and you have a paste right here, you'll have to combine the two and use the mass of the combined, all right? Or what you'll end up with. That's the total mass. So if I have 50 ml of this and 50, and you know the density, you add the two to get the mass, what you'll be using for that. Yes. Andrew, you add the two. Now, let's see, part P, using the result from part A, calculate the envelope in the kilojoules per mole for the solution process. Solution process is, you know, dissolving sodium hydroxide. How many moles did we dissolve? When you look at this, kilojoules per mole, that means when we dissolve this gram, how many grams did we, or how many moles did we have in there? Number of moles of NaOH, using the molar mass of NaOH, I will approximate that 6.50 grams using the molar mass, 1 mole over what? 40.0 grams. So how many moles did we have in there? 6.5 divided by 40. I'm using the molar mass. This is the number of moles, 0.16. All right, 0.16 25 moles of sodium hydroxide. This is sodium hydroxide. So if we divide that, we should get the what? Divide by, this is the number of moles. We divide by the number of moles given in there. It was 72. To 5. Yes, and I get this will be now 0. Not 0. But from what we got from part A, this means 7.23 kilojoules divided by 0.1625 moles. We're looking for a number of moles. And if you look here, it is given off, it is exothermic. So the negative here, 44.4 kilojoules, is exothermic reaction. Why am I putting it negative? To show that the reaction is exothermic. It is given off. How do I know that it's exothermic? By the fact that when you dissolve 6.5 grams in this, and the temperature rose from this to that. That means heat is being given off. If the temperature was dropping, then that is exothermic, and then we're gonna have it positive. In this case, it is negative for exothermic. All right. So that is the typical question on the calorimeter. Most problem you'll see has to do with the calorimeter. You will do an experiment on calorimeter. You have to remember that equation. Rarely will you see the pump calorimeter where you need to remember the heat capacity of the calorimeter. Any question on calorimetry and how to determine the heat of reaction? So if I know the mass of a solution and I know the specific heat, and given the values to find the change in temperature, you should be able to find the heat given in joules. All right. The text uses the specific heat in joules. I've seen some text where specific heat of substances are given in calories. That means your final answer should be in calories. I don't want to dive into or detour into the calorie count. No. So all the heat capacities will be in joules. Now, Hess's law. What is Hess's law? Let me start off by saying Hess was just somebody who just like Avocado came up with an equation or a method or a technique of determining the heat of reaction. You know, we have just looked at the calorimetry and the equation for determining the heat of reaction. However, there are some reactions which are so complex that it is not possible to use either thermodynamic terms given in the text or to use the pump calorimeter or the coffee cup calorimeter for that matter. In that case, we use what we call Hess's law, and Hess's law is simply, you know, a technique of using so many equations to arrive at the final overall reaction. That means for a very complex reaction where it's not possible to use the coffee cup calorimeter or pump calorimeter, we can use many, underline the word many reaction. And it is inconvenient to measure, so it's not possible to measure using a thermometer. We use Hess's law. And it is simple. Don't think that, you know, when we say Hess's law, you know what it's all about. If you know third grade maths, then Hess's law is straightforward. All right, Shadi, let me back up. Somebody was telling me or want me to explain the exothermic, endothermic here. This has to do with the, here, right here. I guess this has to do with the numerical value on my whiteboard. You see, in this problem, well, forget even about A and B, the terms right here. If I read this problem, the way it is, you know, it's straightforward, you know, dissolve. But look at the values here. The temperature rose from 21.6 to 37.8, which means if you look at my thermometer, I don't know if you can see my thermometer in there. So if I measure the temperature of just H2O, it is 21.6. After dissolving 6.5 grams of sodium hydroxide and measure the temperature rose to 37.8. Is it exothermic or endothermic? Is it exothermic, Shadi? Talk to me. Exothermic, endothermic, how do you know the reaction is exothermic? It's by change in temperature. The increase in temperature is exothermic. If the temperature is decreasing, that means endothermic. If you look at the wording on the PowerPoint slide, that means if I have here and I hold it right here, the temperature, or if it's exothermic, my hand will be warm because the heat is being released by the system. It's exothermic. So that means the final answer should be negative, meaning exothermic reaction. Exothermic reaction. If the temperature drops from 37 to this one, then it is endothermic, and the reaction here will be, or the final answer will be positive. I hope the questions will not be technical as such. You have to know when it is positive, especially you'll see multiple choice. One is positive, one is negative. I know you have been in such situation like, or in such dilemma like, which one should I take, you know? You use the right equation, but two multiple choices look alike, same numerical value, but the sign will change. This is exothermic. So next time you have to pay attention when they give you this and they give you positive and negative value, right away, that is exothermic. That's how to determine the heat of reaction. Now, I was explaining what Hess's law is all about, all right? It is a technique of determining the heat of reaction where the calorimetry will not work, okay? And we can calculate using the published. Published, that means the literature values for enthalpy of reaction for several equations, all right? If a reaction in multi-step, you see here series, that means we're gonna be using several equations to get the overall reaction. I don't want to just spend time what is going on here. I want to really get into details on the Hess's law, Hess's law, and how do we calculate the enthalpy of reaction for the final equation. In Hess's law, all right, if you remember the previous one of negative 196 squared divided, there was enthalpy of reaction at the end. But for this, it is not possible. But there's the literature value for this equation, there's the literature value for this equation, there's the literature value for this equation. But we don't know the enthalpy for reaction for this. We need to find using Hess's law. So how do I know that this problem is as Hess's law? You may be asked, use Hess's law to determine the enthalpy of reaction for this, or find the enthalpy of reaction for this, given a series of equation 1, equation 2, equation 3, and equation 4. Then you're gonna find in for final. So you have to do the inspection of each individual reaction. You may be given 2, you may be given 3, you may be given 4, you may be given 5. 5 is great, I'm not gonna give you 5. Maybe 3 at most. Do is convenient, 2 of them is convenient. Pay attention to physical state. So this is how the Hess's law works. You will have to look at the overall equation in question and look at the individual reagent or product and see how the equation has been manipulated. If I look at the this reactant, do I see this one in any of the reactant on the individual? No. It is in last or third equation here, and it means we have flipped the equation. Remember what we said earlier on about flipping the equation? When you flip the equation, the sign changes. I want to bring ethylene on this side, all right, on to make it product. So I will flip the last equation and say C2H4. And since all of them, they are in, I need to write the gas because not all, everything is in gas. Some are solid. Going to 2C, this is carbon and it is solid, plus 2H, and it is what? It is hydrogen gas. This means delta H will now be negative 52.4, 52.4. Why am I flipping the equation? Because I want to have what? I want to have this product to be the reagent in my overall equation. So you flip the third equation. Sometimes you may not flip the equation. You may end up multiplying by a factor. So if I look at fluorine gas and fluorine gas, I do have here 6. So either one of them is multiplied by 4, I don't know, but I don't need to flip equation 2 and equation 1. Equation 1 has fluorine, equation 2 has fluorine, and they are on the reagent side. So I don't need to flip equation 1 and equation 2. If I look at, all right, if I look at equation or hydrogen fluoride, HF, right? It has been multiplied by 4. Where do I see HF? HF is right here. Do I see any other way with HF? Nowhere with HF, right? You see HF right here? It is on the product side. This means the only equation with hydrogen fluoride on product side is equation 1. And it should remain. I don't need to flip that. But I have 4, but I have 2 here. That means equation 1 was multiplied by 2. So equation 1 will look like this. Hydrogen gas will be multiplied by what? Hydrogen gas will be multiplied by 2 plus 2F. And this is gas, by the way. Fluorine gas, this is 2, by the way, going to 4HF, and this is gas. So delta H, I multiply by 4. Remember, when you multiply by a factor, the same factor. So 537 times 2. No, times 4, times 2. And this is negative 10, 70, all right, 74. It is in kilojoules. This is 74. All of them, they are in kilojoules. Watch what I did. How did I figure it out? That is by looking at the overall. Look at the final equation here. It's by looking at the reagent or a product, doesn't really matter. If I look at equation or this CF4, it is multiplied by 2. And if I look at this, I don't need to flip equation 2 either. In order to remain with this on the product side, equation 2 will just remain the way it is, but we need to multiply by 2. So I need to multiply by 2 equation 2 as well. So this is 2C. This is solid. That is solid. Plus 4F2 gas. All right. F2 for gas, going to, remember we are multiplying it by 2, 2F, no, 2CF, 2CF like that, 2CF like that, and 4, it's 4, and this is gas. So we multiply by what? We multiply by 2 also. 680 kilojoules times 2. I'm multiplying it by 2, and this is negative 1360 kilojoules. So if I cancel out what is, to get the overall, which is C2H4 and this gas plus 6F2 gas going to 2CF4 gas plus 4HF gas. Look at, we want to find delta H equals to question mark. It's the summation of all those. So if I look at the product side and the reagent side, this will go away. Cancel what is exactly the same. Hydrogen gas look exactly the same. Look exactly the same. So they will not appear in the final equation. So if I add now everything down, this will come down. And this is what we have right here. T6 right here, all right, T6 right here is 2 and 4. That is what we have, 6 right there. If you look at this 2CF is just right here, and that is what we are right here, is what we are right here, and that's what we are right there. To get this now, you add everything, This means for the overall reaction, I will add 1074 plus 1360 plus 52.4. And all of them, this is negative 2486 point what? 0.4, and it is in kilojoules. It is in kilojoules. This is what we call Hess's law. It will be very easy if you have, all right, two equations. It's very easy. And remember, the physical state. Because if I had liquid H2O and gaseous H2O, I will not cancel just because they are H2O. No, the physical state do matter as well. What I have employed here is Hess's law, and Hess's law is used to determine the overall enthalpy of reaction where it is not possible to use the calorimeter, all right? Or the pump calorimeter, where it's not easy, but you have to use a series. Let me back up to right here so that you understand what this means. You see here, Hess's law, if a reaction is carried out in series of steps, so you will see several equations and you want to find the overall, all right? You'll have to use the Hess's law, such as what we did here. Any question on Hess's law? So remember that. That is what it says. So if you flip the equation, the sign will change. If you divide the equation, I didn't divide here. If you divide, you're gonna also divide. If you multiply, you're gonna multiply by that. I've never seen square root. No. We're not gonna do those crazy stuff like that. All right. I'm gonna start from here next Tuesday. It's now what, 5 minutes to 12. I don't want to saturate your mind today. Let me give you extra 5 minutes today. It's to my calculation, and if you join in late, I want to say that once again, there is a quiz due on Tuesday night. Please complete those the quiz before midnight on Tuesday. That is quiz number 4. I will send out the study guide, but basically what we have been going through, don't let things pile. What do I mean by pile? Like starting all this. If you don't practice Hess's law, if you don't practice how to find the heat of reaction and all those, it will be a toll if you try to study the night before an exam, or just you should spend 2 hours every day. I know time is, it's not on our hand, it's not on our side, but please try to, and especially where the course has been condensed. What's supposed to be covered in 16 weeks, it's just been condensed into 12 weeks. So it's like crushed program. Other than that, I want to stop here and say thank you for tuning in. I hope to see you on Tuesday. I will make also chapter 5 homework available. Please continue practicing on that. The class is dismissed. I will stop sharing my screen, and I hope to see you next week. Thank you and be safe.